Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at structural analysis machines problem. So let's get into it. Okay, so here's the problem. So let's have a look at it and think through it. So yeah, you might look at this and think, well, how do I solve this? Uh, so this is a machine problem rather than a frame. So typically, if it's a frame problem, I suggest that you draw a free body diagram of the whole frame and then work your way through the members. If it's a machine problem, sometimes you can draw a free body diagram of the whole thing, but in this case, it's a bit too complex for that. So the next approach that I would suggest to take is to draw a free body diagram of the member of the machine where the known load is applied. But anyway, I'm getting a little bit ahead of myself. So let's look through the problem. So we've got this motor here that's causing this counterweight to rotate, and as that rotates, it acts on this link here, D labeled, I think D. It doesn't have a label at the other end, but this link on the end of the beam DEF, which causes this to rock and this to move up and down. So if we have a force here of 5 kilonewtons that we need in order to do whatever this pumping unit needs to do, then we need to work out from that the amount of torque that the motor must supply to the counterweight. Okay, so let's work our way through this using my iPad app. So I'm going to be looking down at that every now and again. So assumptions firstly. So let's firstly consider the fact that it's moving slow enough that we can neglect the dynamic loading. Okay, so we can still assume that acceleration is zero. Right? So we can still treat it as an equilibrium problem. And then secondly, that the weight of the beam here is negligible in comparison to the other loads. Now that's probably an oversimplification, and in reality you probably need to take into account the weight of the beam. We're given the weight of the counterweight here as part of the problem, but really I think we'd probably need to include the weight of the beam. But for this textbook problem, we're going to assume that weight is negligible in comparison to the other loads. So let's look at our solution. And I already started talking through the solution previously. So firstly, as always, we need to draw a free body diagram. Now, students, when they're doing these problems, often have difficulty working out, well, what do I draw a free body diagram of? And as I said before, if it's a frame type problem, then typically I would start with a free body diagram of the whole frame and then work my way through the individual members. But if it's a machine problem, usually the easiest way to start is a free body diagram of the member to which the known load is applied. Okay, so in this case, it's the beam here, FED. Okay, so we're going to work our way through that. So we're going to work out the force in the link here, DM. Okay, it's not actually labeled DM, but anyway, that's M for the motor torque. But we're going to work out the force in this link. All right, so we note that it's a two-force member because it's connected only at point D and point M by pin connections. So we can treat it as a two-force member, and then we're going to work out that force as a function of the applied load here. Now you could just put in the number. So I think it was given as 5 kilonewtons. You could just put that in and work out what the force is, but you probably should really get used to carrying these known inputs into your calculations as parameters. Because if you wanted to put this into an Excel spreadsheet or write a program to do this, that's what you would have to do. Okay. So draw our free body diagram of the counterweight next, and then we can apply the link force to that and determine the moment m using the equations of equilibrium. All right, so let's do as we've set up here, draw the free body diagram of the beam DEF. Draw it large, neat and clear. Make sure your witness lines are going to where they're supposed to be going to, and so on. Okay, so start by putting on our known load, which is a force acting downwards at the end of this beam. And then we can start looking at the places where we've removed the things that were attached to this beam or this body that we're now analysing. So over here at point D, we've got a two-force member. So we know the force is going to be along the line that joins the two connecting points for that member. Okay, so 30 degrees to the horizontal there. And I put in here the arrowhead already. But to work that out, we can imagine that we take moments about point E. This force here out on the right, force F, will tend to cause a clockwise moment about point E. So therefore, for this beam to be in equilibrium, the force out here, the unknown force at D, must be causing an anti-clockwise moment. Okay, so we can see that that will have to be down to the right. So that's where that arrowhead came from, and we've just put in there the 30 degrees for reference. Give our unknown force a name, a label, so that we can refer to it in our equations of equilibrium. Then at point E here, so if we look up here, we can see this beam is connected to this A frame here by a pin connection. I'm not sure if it said that in the question or not, but you know, if it's not a pin connection here, then we can't solve the problem and it's not going to rock. So yeah, clearly that's a, whoops, I'm drawing on there. Let me undraw that. Yeah, pin connection. So we have two reaction components, a vertical one and a horizontal one. In this case, it doesn't have to be vertical and horizontal, but they're the most convenient for this problem. So if we look at that, we can see, like we've got arrowheads on here already. So we've got this force coming down, this force coming down. So for some of the forces in the vertical direction to be equal to 0, this one must be going up. And then if you look in the horizontal direction, the only two horizontal forces are the horizontal component of the force FD, which will be going to the right. So therefore, our unknown reaction at E here in the horizontal direction must be to the left. All right, so let's label those as well, so we can refer to them in our equations of equilibrium. And typically when we now start to make use of our free body diagram and use the equations of equilibrium, we will start with a moment equation. And usually the moment equation at the pin joint where two of our unknowns pass through, so they have no moment effect about that point. So we can find one of our unknowns straight away. So I've written that here in symbolic form. Sum of moments about point E anti-clockwise positive equals 0. And just before I do that, I've just shown in here the components of the force FD, just for easy reference. So we've got the vertical component of FD, and if you draw your little right angle triangle here, the vertical component is the adjacent side to this angle. So we use the cos of the angle. So FD cos 30 times perpendicular distance from the line of action to the point we're taking moments about, so times 1.75, and it's tending to rotate anti-clockwise about point E, so that one's positive. So then we can move to our other force, so this force out here, perpendicular distance from the line of action to the point is 2.5, and it's tending to rotate clockwise about point E, so therefore that one's negative. Nothing else causing moments, make that all equal to 0. And we can rearrange it and we can get an expression for the force in the link FD as a function of our applied load F. Now you could just put in 5 here for the known load and calculate this number, and then carry that through the rest of your calculations. But I'm just going to carry this F through here, just So, thinking about, if I wanted to put it in an Excel spreadsheet or a program or whatever, then I can, if I want to work out what load or what torque is required for different loads, I can easily do that without having to go through the whole analysis again. All right, so now let's use our other equations of equilibrium. We've got sum of the forces in the x direction equals 0. So we've got two forces here. We've got our unknown Rex at point E, and we've got the horizontal component of the force at D there. So because it's just the two of them, and I've shown them in opposite senses, I can just write Rex equals FD sine theta, or sine 30 in this case. Okay, so make sure that you don't have just this showing in your solution. You must have the justification for writing this, which is sum of the forces in the x direction equals 0, or in the horizontal direction equals 0. So then we can put in here what we found previously. So yeah, FD equals 1.650 F. So I've just substituted that in there. And I've actually done the maths here to work out that. So I put in 5 in here to calculate what that force is. And then sum of the forces in the vertical direction equals 0. So we have our REY that we're trying to find. We have the vertical component of force FD, which we talked about before, so the cos side, the adjacent side to the angle, minus the force here, our known applied load. So do the maths. So I've just substituted FD, so just substituted this down into here and rearrange that and put in my 5 kilonewtons that was given for F, and I've solved for REY. Right, just indicated that there are some answers that are required. So now I draw a free body diagram of the counterweight. Right, start thinking about the loading. So on the counterweight here, we've got FD, which is equal and opposite to what we had up here. So what the link does to the beam does equal and opposite to the link, and then down here the link acts on that counterweight. All right, so just put in that angle there, and I've just put in that it's equal and opposite to FD on the free body diagram of the beam DEF. And we've also now need to put on our torque that's applied by the motor, and we've got the weight of the counterweight out here. And at A, we've got a pin connection, so we've got reactions horizontal and vertical there. So taking moments about point A, we can work out what M is going to be. All right, so WG times 0.65 plus 0.5 times cos 30. So what I've done here is to find the perpendicular distance from the line of action of WG to point A. Okay, so this length here from A to G is 0.65 plus 0.5, and we want this length at the bottom of that triangle down here. This angle is 30. This is the adjacent side to the 30. So this length from the line of action perpendicular to that to the point here is 0.65 plus 0.5 cos 30. Okay, and that's tending to rotate clockwise. Right, so that's negative. And then we have the force here, FD, and its perpendicular distance. So this is 30 degrees here. This is 30 degrees here. So this length here, 0.65, is the perpendicular distance from the line of action of FD to this point where rotating moment's about. And it's tending to, where's FD? Tending to rotate anti-clockwise about point A, so it's positive. And then we have the moment, which is applied by the motor to the arm in the clockwise direction, so that's negative, all equal to 0. And then we can rearrange that, or before we rearrange that, we're just putting in some numbers here. So we were given that the counterweight weighs 300 kilograms. I just converted here so we get an answer of in kilonewtons, because our load out here was given as 5 kilonewtons. We worked out before that FD was 1.65 times F, and F is 5 kilonewtons. So rearranging this equation here, so just taking M over to the other side, we have FD times 0.65. We just need to substitute this in here. So that's where this is coming from. And then we also have minus WG, which is 0.39.81 times 0.65 plus 0.5, which is 1.15 times cos 30. So we can do the maths and we get that our torque that we need to apply to the motor to have to generate the force in whatever is down here of 5 kilonewtons, we need to have 2.3 kilonewton meters of torque exerted by the motor. So if you also determine the reactions at A, I'm not sure if that was answered, was asking the question or not, but just to a bit more completeness of our solution, sum of the forces in the horizontal direction equals 0. So here we have RAX. The only other horizontal force is the horizontal component of FD. So that will be the opposite side here of this triangle, so sine 30. Put in our values, right? Substitute again for FD. Right, you could have, as I said before, you could have worked out the value of FD if you like, but I've just carried through the F. So we got 4.13 kilonewtons there. And then sum of the forces in the vertical direction equals 0. We have RAY going upwards, so positive. FD cos 30, the vertical component of that force there, also going upwards, so positive, and WG coming down, so that's negative as we write it in the equation of equilibrium. So rearrange all that, substitute in as we need, and we can solve for the unknown force RAY. So you can see here I've got a negative number, which indicates that I put the sense of RAY incorrectly on my free body diagram. But that's okay, I just leave it as it is. I don't need to change my diagram here. I can just go over and look and see, right, RAY is minus 420, so it's actually in the opposite sense. If you really want to, you can do something like this. You can say, i.e. force is actually that way in your solution, right, because it's negative. All right, so that's the end of the problem. Hopefully that was helpful and interesting. Kind of a little bit of a difficult problem when you first look at it. But as I've said before, if you work through it slowly and carefully and diligently and with discipline, making sure that you draw your free body diagrams clearly, large, neat, and then apply your equations of equilibrium. Make sure you obey Newton's third law when you're drawing the forces where you've disconnected two of the bodies that were part of the frame or machine, then you should be able to get through the problem. All right, that's it for now. See you next time. Bye.